through pipes, circular ducts, or otherwise circular ducts. Now I consider a pipe of length L. Flow is in this direction. Let m dot be the mass flow rate of the fluid in kg per second. Cp is the specific heat in joules per kg Kelvin. This is the rate of heat transfer between the wall temperature and the fluid temperature. The flow shall be called laminar if Reynolds number is less than 2000. The flow is turbulent if Reynolds number is greater than 4300. So this 2000 is called lower critical Reynolds number. 4300 is also known as upper critical Reynolds number, where Re is Reynolds number, which is inertia force divided by viscous force, which is given by Vd rho by mu or Vd divided by nu, where nu is kinematic viscosity of fluid given by mu by rho in meter square per second. If 2000 less than Reynolds number less than 4300 implies, it means it is meant that flow is in transition from laminar to the turbulent domain. Because once the Reynolds number is greater than 4300, the flow becomes turbulent. Most of the flows in circular ducts would be turbulent, because even at the Reynolds number of 4300, the flow would be becoming turbulent. Whereas in the case of flat plates, for the flow to be called turbulent, the Reynolds number should cross 5 lakhs, 7 lakhs, 5 to 6 lakhs, the transition would begin. Up to 5 lakhs, the flow is laminar. Therefore, I could say that the flow would easily become turbulent in the case of the flow through ducts or pipes. If you take a differential length of the pipe, consider differential length of pipe dx. If dq is the differential heat transfer rate for this length dl, then for length dx, then dq is equal to mass flow rate into Cp into change in differential bulk mean temperature. If you integrate that, you will get h 2 pi r dx, that is a flow area, into T wall minus bulk mean temperature, where Tw is equal to wall temperature Tb is equal to bulk mean temperature. If you integrate both sides, we get Q is equal to HA Tw minus Tb, where A is the total surface heat transfer area. Please note that in the above equation dq is equal to m dot cp dtb, that indicates the change in enthalpy of the fluid as it flows through a distance of dx, whereas right hand side h into 2 pi r dx is the area of heat transfer for a length of dx. T wall minus Tb is the temperature difference between the wall and the bulk mean temperature of the fluid. Where A is the total surface area, I can consider this as pi dl, where d is the diameter of the pipe and l is the length of the pipe. The empirical formula that is widely used to calculate convection heat transfer coefficient for turbulent flow through pipes is Nusselt number is equal to 0.023 into Reynolds number to the power of 0.8 into Prandtl number to the power of n, where Nu is equal to Nusselt number given by Hd by K. Re is equal to Reynolds number given by vedi0 by mu, and Pr is equal to Prandtl number given by mu Cp by K. N is index 0.4 for heating of fluid and 0.3 for cooling of fluid. So in the elaborative manner we can write that Hd by K is equal to 0.023 into vd0 by mu whole to the power of 0.8 into mu Cp by K whole to the power of n. N may be 0.4 or 0.3 based on whether fluid is getting heated up or getting cooled. This is strictly holding good for turbulent flow through pipes. If the flow is not through a circular cross section, then the heat transfer correlations, particularly for Nusselt number, is based on the hydraulic diameter dh. I can write if the channel through which the fluid flows is not of circular cross section, then the heat transfer correlations should be, the calculation of Nusselt number वगैरह should be based on hydraulic diameter dh defined by dh is equal to 4a by p, where a is cross sectional area of flow and p is wetted perimeter. Now I shall do a small problem on this particular forced convection heat transfer through pipes. The problem is given like this. Air at 2 atmospheres and 200 degrees centigrade is heated as it flows through a tube with a diameter of 2.54 centimeters at a velocity of 10 meters per second. Calculate the heat transfer per unit length of tube if a constant heat flux condition is maintained at the wall and the wall temperature is 20 degrees centigrade above the air temperature all along the length of tube. How much would be the bulk temperature increase over a 3 meter length of tube? The solution to this problem could be given like this. First of all, let us calculate Reynolds number of the flow, and then we shall decide whether the flow is laminar or turbulent. Accordingly, we will choose the formula to calculate the convection heat transfer coefficient. First of all, let us calculate Reynolds number given by vedi0 by mu. Now, the properties we pick up at bulk temperature of 200 degrees centigrade, bulk mean temperature of 200 degrees centigrade, or density can be calculated as P by RT, that is P is 1 atmosphere. You should convert into pascals, 287 joule per kg Kelvin, that is 200 plus 273, it becomes 473, that is 1.493 kg per meter cube. That is the density of air at bulk temperature of 200 degrees centigrade and pressure of 2 atmospheres. Prandtl number is given as 0.681. Dynamic viscosity of air is given as 2.57 into 10 power minus 5 kg per meter second. Thermal conductivity K is 0.0386 watts per meter degree centigrade. Specific heat is 1.025 kilojoule per kg degree centigrade. Therefore, Reynolds number is given as vedi0 by mu 1.493 into 10 meters per second, velocity 0.0254 divided by 2.57 into 10 power minus 5. That comes to 14,756. Clearly the flow is highly turbulent. So the flow would easily become turbulent in the case of the flow through pipes once it crosses 4300 Reynolds number. Therefore, I can use the Mcadams equation. Mcadams equation or Dittus-Boilter equation, that is given by Nusselt number is equal to HD by K is equal to 0.023 into RE to the power of 0.8 PR to the power of 0.4. Here the fluid is getting heated up because wall temperature is more than fluid temperature. Fluid is getting heated up. I should choose the N value as 0.4. Therefore, that is equal to 0.023 into 14,756 Reynolds number. Prandtl number we know that 0.681 to the power of 0.4. Therefore, H is equal to K by D into Nusselt number. K is 0.0386. 42.67 is the Nusselt number, divided by diameter is 0.0254 centimeters. It comes to 64.85 watts per meter square Kelvin. That is a force of convection with air. Therefore, the heat flow per unit length is given as Q by L is H pi d HA delta T, TW minus bulk temperature. That is given as 20. Throughout the pipe, length is given as 20. That is 64.85 H into pi into 0.0254 into 20 degrees centigrade. It is given in the problem that the wall temperature is 20 degrees centigrade above the air all along the length. So Q by L comes to 103.5 watts per meter. This is the rate of heat transfer per unit length of the pipe. Now we can write the energy balance. Energy balance equation for 3 meter length of the pipe. For 3 meter length of tube or pipe. Q is equal to rate of heat transfer from pipe to from wall to air is equal to rate of change of enthalpy of air given as mass flow rate of air, Cp of the air, temperature rise of air, or increase in the bulk mean temperature of air. We know that the rate of heat transfer is Q, that is given as Q by L into 3 meters. That is 103 into 3 into 103.5. This is equal to mass flow rate if it is rho AV, rho into pi by 4 d square into velocity of flow, that is mass flow rate. Cp is given, and delta T of air, bulk increase in bulk mean temperature of air for 3 meter length of the pipe, which is to be calculated. Therefore, delta T increase in temperature of air for 3 meter length is calculated as 40.04 degrees Celsius. Density is given, diameter is known, that is 0.0254, velocity is also known, and that is 10 meters per second. Cp is given. Please keep the Cp in joule per kg degree Kelvin, because Q we have calculated in watts per meter per unit length. Hence the problem. Now I shall solve a problem given in GATE 2005 for 4 marks. There are 2 questions involved here in this problem, linked answer questions. An uninsulated air conditioning duct of rectangular cross section 1 meter into 0.5 meter rectangular cross section, carrying air at 20 degrees centigrade with a velocity of 10 meters per second is exposed to an ambient of 30 degrees centigrade. Neglect the effect of duct construction material for air in the range of 20 to 30 degrees centigrade. Data are as follows. Thermal conductivity is equal to 0.025 watts per meter Kelvin. Velocity is equal to 18 micropascal second. Prandtl number is equal to 0.73. Density is equal to 1.2 kg per meter cube. The laminar flow Nusselt number is 3.4 for constant wall temperature. Conditions for turbulent flow, Nusselt number is equal to 0.023 Re to the power of 0.8 Pr to the power of 0.4. Then the Reynolds number for the flow is A 444, 890, 4.44 into 105, 5.33 into 4.44 into 10 power 5, 5.33 into 10 power 5. B. The next question is the heat transfer per meter length of duct in watts is A 3.8, 5.3, 89, 769. The solution to this problem, let us indicate the problem in a pictorial manner. This is the rectangular duct. This is 1 meter, this may be 0.5 meter. Air is carried at 20 degrees centigrade and the temperature of the duct could be taken as 30 degrees centigrade because effect of duct construction material is neglected. So whatever the ambient temperature of 30, that could be taken as duct temperature itself. So there is heat transfer from the duct to the flowing cold air 20 degrees centigrade with a temperature difference of 10 degrees centigrade. First of all, let us have to establish what is the Reynolds number value, and based on that we will have to choose the formula whether flow is laminar flow. If it is laminar flow, we have to choose 3.4 Nusselt number. If it is a turbulent flow, we have to use the other formula. First of all, let us calculate Reynolds number. Reynolds number is given by Vd rho by mu or Vd by nu. Vd rho by mu. Here d is characteristic dimension because it is not circular. It is a characteristic dimension. Here the characteristic dimension in meters could be calculated as 4a by p, where a is cross-sectional area, that is 1 into 0.5, perimeter is 2 into 1 plus 0.5. We will obtain characteristic dimension in meters, based on which Reynolds number is calculated as what is the velocity given with a velocity of 10 meters per second. Characteristic dimension is already known. Density is given as 1.2. Mu is, please check the data here. It is not velocity here, it is viscosity. I had wrongly mentioned velocity, it is viscosity. Please check that. 18 micropascal second, that is 18 into 10 power minus 6. Micro means 10 power minus 6. So we get the Reynolds number. So answer is obtained as 4.4 into 10 power 5. Answer is C. So we have to use the flow as a turbulent. So for turbulent flow, because Reynolds number is much greater than 4300, for turbulent flow, Nusselt number is equal to 0.023 into Reynolds number to the power of 0.8 into R to the power of 0.4. Here the air is getting heated up, therefore N value should be taken as 0.4. So Nusselt number is HD by K is equal to 0.023 into 4.44 into 10 power 5 whole to the power of 0.8 into Prandtl number is already given as 0.73 in the data of the problem to the power of 4. We can obtain H value here in watts per meter square Kelvin. Thermal conductivity is also given K 0.023. We have calculated the characteristic dimension earlier, D also known, so H is calculated. Heat transfer per unit length is equal to H A delta T. What is the unit length? Per unit length area of heat transfer, H into perimeter into length, 2 into 1 plus 0.5, that is perimeter, into length is 1 meter. Delta T is 30 minus 20. We will get the heat transfer rate in watts per unit length of pipe per meter length of duct. Hence the problem. H is already calculated above. Substitute the H value, we get the heat transfer rate Q per unit length of the tube or duct. Now I shall solve an objective question given in GATE 1999. If velocity of water inside a smooth tube is doubled, in the turbulent flow heat transfer coefficient between the water and the tube will A. remain unchanged, B. increase to double its value, C. increase but will not reach double its value D, increase to more than double its value. The solution to this could be given as: for turbulent flow through pipes, Nusselt number is 0.023 into Re to the power of 0.8 into Pr to the power of n. So Nusselt number has the formula of Hd k by k 0.023 into Vd rho by mu to the power of 0.8 into Pr to the power of n. Implies everything else being constant, H is directly proportional to the V to the power of 0.8. Implies if velocity is doubled, H increases by 2 to the power of 0.8 times, which comes to 2 to the power of 0.8 as such. So it comes to 1.74. So answer is C. Increase but will not reach double its value.